Good morning, everybody. I'm here today to present the work of mainly Mr. Olivier Ballet, who worked for the past 6 months with us on a tether-based aerodynamic deorbiting system. Mr. Ballet preferred to be in Tanzania today with the lions. I perfectly understand his reasons, so I gladly accepted to give this presentation. So what we started designing is in fact not a CubeSat. We looked at all the advantages of the CubeSat, and then we decided, can we build a non-satellite that uses CubeSat subsystems as much as possible, but something that can also support a payload of 5 kilograms, 5 liters, and 5 watts. And we call this OS4 Lab. So we started designing this. Our intention is to make it an open design, to share the design when it's complete with everybody. And we started making the analysis. Then at 700 kilometers of altitude, when we made the analysis, we saw that it stays in orbit approximately 35 years. And then at the same time, Mrs. Dorina Andoni, the space lawyer that you met yesterday, she told to us, guys, this is not acceptable. You have to do something. You have to respect the 25 years rule. So we decided to have a deorbiting system. So we started looking into the options, inflatable systems, micropropulsions, etc. But then we thought it might be good to use a simple and reliable system which is based on tethers. So we can have the drag capabilities of a solar sail and also use the gravity gradient advantage of the tether. It would be a passive system, so we don't need a propellant. It would be a low-weight, low-cost system, and of course we intend to have something smaller than usual tethers. So not in the order of kilometers, but in the order of a few meters. Then we designed a tether which is between 3 and 5 meters, and here you see the lifetime with different comparisons. If we don't have any tether, a tumbling 3-unit CubeSat would remain in orbit for maybe 40 years, and with tethers of 3 meter and 5 meter length, you can reduce this to 5 years or 3.5 years. So what is the mechanism there? What are how do we try to keep it stable and make it work? Imagine that you have a satellite, a certain mass, and there's another smaller mass that you connect with a tether. So in this configuration, the forces acting are centrifugal force and gravitational force, which should be in equilibrium normally. So, but when you connect them with a tether, because you move the center of mass slightly above, and then you change the rotational speed of your system, then the centrifugal force can be a little bit bigger. So it means that there would be a tension in the tether, keeping it stable. This is a statistical analysis. So this was the idea that we came up with, a tether connected to a small mass at the end. The small length of a couple of meters, it means small forces in play. Both the tension force and the aerodynamic force acting on the tether is in the order of 10 to minus 6 newtons. Of course, things do not stay stable all the time. If you have a drag acting on your tether, then it's going to push the tether in the other direction. It is going to create a certain angle, and then your effective area will be reduced. And this, of course, we have taken this into account in our analysis, and with the angle changing and with the effective area decreasing, of course, the drag force, the overall drag force is also decreasing. And then we started comparing the tension force versus the aerodynamic force. And at higher altitudes, the aerodynamic force is very low, and it increases as it goes down. Then the tension force is opposite. It's higher at the beginning and it goes down. And at a certain altitude, what we call equilibrium altitude, you can assume that the tether is in 45 degrees. And below this altitude, the things will be chaotic. So it's difficult to talk about the stability of the tether system anymore. And, but still there will be an aerodynamic force, it will be completely tumbling, and then it will be going down. So the idea would also be to have this equilibrium altitude as low as possible. So we started looking at different designs, at different altitudes. What if we make it longer or shorter? What if we put more mass or less mass, etc.? And we try to make some analysis. For example, the mass of the tip. How does it affect our studies? So we tried different configurations with 200 grams and 500 grams. And then what we see is if we increase the mass, it does indeed take the equilibrium altitude lower, which is a plus sign. In fact, in the overall, the mass at the tip does not have any effect on the total lifetime, but it has an important effect in the stability. It allows us to keep the tether in a stable configuration for a longer duration. Then this is just the result that shows how it changes the effective area if you have two different masses, 200 gram and 500 gram. And so if you want to decrease the time of deorbiting, it is better to play with the length of the tether. So here are some results, some typical results. As I said, our primary orbit is sun-synchronous orbit at 700 kilometers. And if we don't have any precaution, we can stay there between 35 and 40 years. But if we have the system with 250 gram and 3 meter tether length, it's 5 years. And it's possible to decrease this down to 3 years with 500 grams and 5 meter. Although this is not our intention, we also checked that the same concept would work for a bit higher altitudes, like 850 kilometer altitude. So instead of an original 100 years of lifetime, you can reduce it to 20 or 13 or even 7 years. Then, of course, the next step is what to use as the tether material, how to design it, and so we looked into the into the market, and then the choice was kind of obvious for us. Kapton is a good material, it is space qualified, we can use it, we can find it, and then it's light, it's thin, it's resistant to the space environment, it's not metallized, and then we already had some equipment and we started testing it. What we have not done yet is how to inject or how to deploy the tether. So this is ongoing work, it's being designed. Either we can very basically assume a spring system that is just going to pop up the tether, but then of course for that we need to make more dynamic analysis to see the fluctuations if we need a damper, etc. But one other idea could be just using a micromotor to inject it very slowly, let's say the 3 meters in 1 day or in half a day, to assure that it's always in a good stable configuration. So this has the advantages of stability, but it also has the disadvantage of maybe reliability, because you want to use this system, I don't know, maybe 3 years after you put your satellite in orbit, and you have to make sure that it is going to function after 3 years. So that's one of the important things. But we did our market survey, we know that the solutions exist. So now the next step is to design this mechanism, which can of course also fit into a CubeSat, and then it can be used by the community. As I said, up to now we did only static studies, and the future work, what is remaining now, is more dynamic studies. Can we just simply use a spring damper system? Do we need a more sophisticated system? And at the same time, more foldability tests with the Kapton material and stability over time, and these kind of analysis is necessary. So as we have more progress, of course, I will be happy to indicate that to you. So I thank you for your attention.
Any questions? Go back here.
Hi Tim. Have you looked at the probabilities of micrometeoroid impact and also investigated options that you can have with your cell material to compensate for that?
I didn't understand. What effects did you say?
Micrometeoroids, so the chances of hitting small particles with your membrane.
No, not specifically onto that, but one of our motivations was instead of using a 5 kilometer long tether, to use only a 3 meter long tether to avoid any unwanted collision with any other space object. We didn't think of meteorites, but we just say we have to decrease the overall area by still making it feasible.
Okay, but just something to consider in the future. I mean, I think the chance, it's quite likely that you'll have, like millimeter sized particles impacting your membrane, and without ripstops, very thin kapton might tear and might open it.
That's correct, thanks a lot. One very rough thing that we did is when we are calculating the effective area, we assumed, in fact, we used an efficiency of 60%. So we calculated the best efficient area, and we said, but we might be losing it because of some misalignment, etc., or maybe because of these reasons. And so we assumed 60% efficiency, and the results given are by this efficiency.
Okay.
Okay. Peter from the Swiss Space Center. In one of your very first slides, you showed that you want to develop your own platform. Why don't you just use an 8 or 12 unit CubeSat platform instead of that?
Yes, that's a good point, but in fact this is kind of, roughly speaking, this is 20 by 30 centimeters. But when we talk about a 12 unit platform, in fact that's kind of what we are doing, but we also want to redesign the structure so that we can accommodate bigger payloads. So we don't want to divide it in the middle by some structural elements if possible. And then the main problem is the ADCS. So it needs to be redesigned. We cannot use the existing CubeSat ADCS. But otherwise, that's kind of what we are doing, in fact. All other systems are standard CubeSat systems.
Are there other questions? Yeah, back here again.
Hello. I've got a similar question to the one from the previous presentation. How do you ensure that your tether will not turn into the direction that is the thinnest? So it will not be facing like with the whole surface in the direction of movement, but to be with the thinnest part.
Yes, so the satellite will of course have ADCS, and that's an important point. So before we deploy that, we have to make sure that the deployed additional surfaces will be facing that direction. But then afterwards, the intention is not to control this anymore by the ADCS, but by relying on the design, on the stability, so basically the difference between the tension force and the aerodynamic force down to the equilibrium altitude. And below the equilibrium altitude, we will probably lose all stability, and it will just be a chaotic big structure that is losing altitude. But if we are working on 3 to 5 years of lifetime, this is fine. But then this system wouldn't work if you really want to go very fast and in a very stable position.
Okay, any last questions? Great, well, thank you.
Thank you.